Hey everyone, and welcome to this explainer. I am absolutely thrilled you're here today because we're about to take a journey straight into the brain of your devices. We're looking inside the machine to really demystify the fascinating and honestly brilliant architecture of computer memory systems. Get ready to see how all these invisible parts orchestrate perfectly behind the scenes.
Right off the bat, let's talk about a scenario we all know way too well. If your CPU is so blazingly fast, like capable of executing billions of instructions per second, why does your computer still lag when you try to open a massive program or a huge file? Well, the truth is, while our processors can think almost instantly, finding the actual data they need to think about, that's the real bottleneck.
So here's how we're going to map out this data workspace today. We'll start with the memory speed problem. Then we'll move down the memory hierarchy pyramid. After that, we'll uncover the secret weapon that is cache, contrast the physical chips of SRAM and DRAM, and finally, we'll explore the brilliant illusions of virtual memory and RAID. Let's get right into it.
Kicking things off with Part 1, the memory speed problem and the processor bottleneck.
To really wrap our heads around this, imagine your CPU is a brilliant, hyper-efficient worker sitting at a desk. If they have the documents they need right in front of them, boom, they work miracles. But if they have to stand up and walk all the way across town to a warehouse for every single piece of paper, well, the whole system just grinds to a halt. CPUs are incredibly fast, but data retrieval is the ultimate bottleneck. The entire discipline of computer organization is basically obsessed with this one massive challenge. How do we keep that blazing fast processor constantly fed with data so it doesn't just sit there twiddling its thumbs?
So, how did engineers actually solve this? That brings us to our next section, the memory hierarchy pyramid, where it's all about balancing cost, speed, and capacity.
This brilliantly illustrates our roadmap. At the very peak of our memory hierarchy, we have registers and inboard cache. These are tiny, but man, they are incredibly fast. Then as we move down through main memory and further down to outboard storage like magnetic disks, and finally offline storage at the very bottom, the spaces get much larger, but they also get significantly slower.
Walking down this pyramid, you really see the fundamental trade-offs at play here. As we move from top to bottom, the cost per bit decreases, meaning memory gets cheaper. Because it's cheaper, capacity increases, allowing us to store way more data. But, and here's the catch, access time also increases, meaning the speed goes down. And because of that slowdown, the frequency of access by the processor decreases too. It's a massive balancing act. You simply can't have memory that is dirt cheap, massively huge, and lightning fast all at the same time.
Which brings us to arguably the most vital layer for speed, cache, the secret weapon for keeping data close.
If our CPU is that efficient worker, the cache is the small, super fast bookshelf sitting directly on their desk, and it works almost like magic thanks to this essential concept, the principle of locality of reference. Basically, this is the tendency of a processor to frequently access a small, concentrated portion of memory. Because of this tendency, the computer can essentially guess what data and instructions you'll need next and keep them right there in the fast cache. It's literally predicting your next move to save time.
But how do we organize that small bookshelf? We use mapping techniques. Let's contrast two main ones. First, there's direct mapping, where a block from main memory maps to only one specific cache line. It's kind of like a rigid, predetermined filing system. On the flip side, we have fully associative mapping, where a memory block can be placed in any available cache line. This is highly flexible, but it's a much more complex way to utilize the workspace. Oh, and as a quick side note, computers often use a middle ground called set associative mapping to perfectly balance this raw speed with flexibility.
What's really interesting here is how that associative mapping actually functions. Simultaneous comparison is the key. When the CPU asks for data, the hardware takes a tag and checks it against all the cache tags at the exact same time. If there's a match, boom, it's a cache hit. This simultaneous checking is exactly what allows the computer to find the data instantly.
But of course, our tiny cache desk inevitably gets full, right? When that happens, the system has to kick old data out to make room for the new. It handles this using clever cache replacement algorithms. The three most common are LRU, FIFO, and LFU. LRU, or least recently used, evicts the file that's been gathering dust the longest. FIFO, first in, first out, just boots whatever was loaded first. And LFU, least frequently used, replaces the block that gets used the least often. It's all about maximizing our chances of keeping the most useful data right there on the desk.
Okay, let's step into the physical realm. Section 4, SRAM versus DRAM, the physical makeup of memory.
You might be wondering, why don't we just build the entire computer out of the fastest memory? Well, contrasting these two really answers that. On one hand, SRAM, or static RAM, uses stable flip-flop logic gates. Think of it like a light switch that stays on. It requires no refreshing and is lightning fast. This is what we use for cache, but it's super expensive and a lot less dense. On the other hand, DRAM, dynamic RAM, stores data on capacitors. These are like tiny, leaky buckets of electricity. They require constant, periodic refreshing so they don't lose data, which makes them slower. But they're way less expensive and much denser, which is exactly why we use DRAM for main memory. We absolutely need both to balance the scales.
Now that we've got a handle on the hardware, let's shift over to the software tricks in our final section: virtual memory and RAID, the illusions of storage.
This is how computers brilliantly bypass their physical limitations. Let's compare our two main illusions. We already know cache memory is designed to combine high-speed access with large capacity by storing copies of frequently used data. It basically fakes having incredible speed. Virtual memory, on the other hand, allows programs to use a logical address space that is way larger than the actual physical RAM. It uses virtual addresses entirely managed by the system to fake having infinite space. Both of these illusions are absolutely essential for modern computing performance.
And then, right at the very base of our memory pyramid, we have RAID, which stands for Redundant Array of Independent Disks. The crucial takeaway here is that RAID gives us a way to combine multiple, separate peripheral disks together. We can literally take cheap, slow magnetic disks and group them to scale our storage architecture even further. This gives us maximum capacity and, crucially, protection against hardware failure.
When you step back and look at the whole picture, it truly is a symphony of hardware and software. Registers, SRAM caches, DRAM main memory, virtual memory systems, and RAID storage. All of these completely different technologies are orchestrating seamlessly behind the scenes. They work together to give you, the user, the illusion of a computing machine that is simultaneously infinite in size and instantaneous in speed.
Which leaves us with a pretty massive, fascinating question to wrap up today's explainer. As we push the boundaries of computing, how will future technologies like artificial intelligence or quantum computing force us to redraw this entire memory pyramid? Will the hierarchy flatten out? Or are we going to see it grow entirely new dimensions? It's definitely something to think about. Thank you so much for exploring the machine with me today, and keep your curiosity focused on what comes next.